So in today's class, I will teach about I2C programming, and here we will send these values, that is second, minute, hours, Sunday, that 14 June, and then year. Here only the last 2 bits will be stored in the RAM memory of slave device, that is the slave device GS1307, that real-time clock device. And this whatever we are going to send from the master through the I2C bus will be sent bit by bit to this memory address locations. And this 55 second is having hex value 0x55, and 5 is 101, and this 5 is 0101. So this is the binary value of this 0x55, that means 55 seconds. So 58 minutes, hex value is 0x58, and this 5 is 101, and this 8 means 1000. So this 58 is having this binary values, and so like that all this will have this much binary values, and this is your hex values, and this binary values will be sent to this particular memory RAM address, and this is address of 1 byte each. 1 byte contains 7 bits, so this binary value containing 8 bits will be stored in this 1 byte locations. This is just address of 1 byte. So those data will be sent from CORTEX processor through the SG line, this line, and then will be stored in that RAM memory address of this slave device GS1307. So let's write the code. I'm including the library of TM4C 123Js 6pm.h, that I'm including the library of Java microcontroller, that CORTEX M4 bus, and I'm defining the slave address. This is usually X68 for that slave device GS1307, the real-time clock device. And here I'm writing the I2C initialization functions. I will explain this little later, and then I will define here I will write here the I2C1 byte write function. Here we are going to send this function will send the address bit and the data bit from the master to the select device, and we will pass the select address and then memory address and then the data. Okay, I will also explain this little later, because if I explain this separately here, then the flow in explaining the code step by step will be separate, and so you won't be able to you will jumble up. So because of that, so let's come to main function first. We will just take an array containing 7 values. We will just copy the value we are going to send. The second values, meaning values. And then we will copy this over Sunday 14 June 2026. 14 is this 14, June is 6 months, starting from January, February, March, April, May, June. So it will be 0x06. Here will be only 26 because it store only the last two digits. Last two digits is 26. By the select device TS1307. This is select device memory location, so only the last two bit will be stored. Because of that, we write 0x26. And Sunday is first day of the week, so we write here 0x01. If that is Monday, then 0x02. 13 is hour, that means 1 p.m. You can write any whatever you want, but here I'm writing like this. You can change it as you wish. So I'm passing 7 values. And here in the next line we are just writing an array containing 7 values. And here in the next line I want to call the I2C initialization functions. So since I didn't explain it, so let me write here. So system control is using the I2C GPIO register. And what does this I2C GPIO does is just we will set it to 0x01. And what this function does is, this is 0, this is 1. This also GPIO, what this function does is supplying the clock source to any one of the bit from the 0 bit to the 7 bit of this 32-bit register RCGC GPIO, so that we can we can choose any port. Since I'm supplying the clock source to the bit 0 by setting it the bit 0 to 1, so I'm setting port A, or GPIO A, so that we can use in our code, or this projects. This is not project, this is just simple projects, we can say that. And system control is now using RCGC I2C, and setting it to 2x02. This the system control is now using this register RCGC I2C, and for this register 2 is supplying the clock source to the pin in either of the pin from 0 to 3 in order to choose any I2C version you want to set to be used in your code. So we set it to 0x02, 0x02 in hex is 0010, so this will be 0010. So I'm putting 1 here, that means setting this bit 1. So I'm choosing I2C 1. You can choose any one of the I2C zeros, or I2C 1 or 2 or 3 by setting it here. But here I'm choosing I2C 1. I2C 1. And as I'm choosing GPIO E, I will use GPIO E, and then we have SAL resistor, and C is 11000000, 0 is 00. So GPIO E, now using AFSEL. AFSEL is 32-bit register, and this register is saying to bit this particular bit 6 and 7 to be used as an alternate function. That means for many variable of functions, that means for you can use for many function of whatever you want, either for SPI, I2C, UART, etc. And then here this is FF. FF means 1 1. So this one is negation. Negation of 1 1 will be 0. So I'm clearing this bit number 6 and 7 of this port control register, because see the next line. Because I want to I'm clearing this bit 6 and 7 here. So because I want to put 3 values in the bin 6 and 7 of this port control register. I'm clearing this 6 and 7 of this port control register and putting the value 3 because this will make the GPIO pin 6 and 7 6 and then 7 will be used for I2C. Pin number 7 for I2C SGL line and pin number 6 for I2C SCL line. And this port control, if you put other value, it can be for PWM or GPIO for other functions. But here we are putting this 3 so that it is this pin we are putting 3 here because so that this pin can be used for is now going to use for I2C only. And then function C is 1100 and 0 is this. So that means I'm setting the bit 6 and 7 for digital. Because here everything is digital, and also in this function I'm not going to do any kind of analog operation here. It means this and 0 means this. Here this is open drain. So here I'm setting the bit 1, the bit 7 to open drain to follow the open drain system pattern, because this bit 7 is the I2C SGA line where it has to connect with all those master and slave, and this master and slave connected to SGA line we prefer for those devices that output circuit is connected to the low level function transistor. This is prefer in this I2C system, because if we allow master, if we allow device to some device like whose output circuit is connected to a high level transistor, and then mix up with low level function transistor, then sometimes the high voltage from the high output transistor, high output function transistor will may cause the power may may sometime jump. There may be directions as another one is high and another one is low, so it may flow from high to low and then cause short circuit. Because of that, we don't want any kind of short circuit. So all the device that is going to operate in this system, we prefer it connected to low level transistor circuit in the output section of the device. MCR, we are using the I2C one is now using MCR resistor to set a particular device as its master. By setting the bit D4, one is this and this is 2. By setting the bit D4, we are setting the particular device as master. Let me show you this one. By setting the bit D4, we are making the device to operate as a master function, enable the device to operate as a master. By setting this bit D4 bit. Is it holding too long? And then your I2C1 implies MTPR equal to 7, because MTPR equal to 7, if we set, then the data will be transmitted at the rate of 100 kilobit per second. Because of that, so in this this is I2C initialization functions. Here, first of all, we choose the particular port, and then the I2C versions, and then the port we have chosen. For that port we have chosen the bit 6 and 7 is set for alternate functions. That means alternate functions means it can be used for any functions like I2C, SPI, UART, whatever. And then we are clearing the bits 6 and 7 of this port control resistor so that we can put this value 33 in this port control resistor, so that the bits 6 and 7 of this GPIOA can be used for I2C SCL and I2C SG. And the next line is then. So we are setting this bit, that means this same bit, as digital, so that it can be used for any digital operations. And then this ODR, setting this bit to follow the open drain system. So that all the device connected in this system may have an output connected to low level function transistor, so that there is no any kind of short circuit or anything unwanted not happen in this system. And then we are choosing here the master device, and this is transmission rate of data. setting it to 100 kilobit per second. And here, okay, we will write I2C address and data transmit functions. But before it, okay, I want to write, okay, another, okay, functions. This one is not related to I2C, but just let me write because it is needed if I want to use any kind of float or table values in the code. Because the system is using CPAC or register and setting it to 00. Because setting it to 00 F, this F value is 1111, and this 2-bit will set the coprocessor, okay, 11, and this bit will set the coprocessor 0, and this setting of the coprocessor 11 and 10 is necessary in order to use the floating point unit of the system to be used by the CORTEX coprocessor, because sometimes we use the float and, okay, double value in our code. So that's it, and it is only for using the floating point unit by the CORTEX processor. And after this, we will, okay, send the we will write the functions for sending the address and data in the I2C bus. So this is the function, and we will pass the slab address and then memory address. Because this is required in the function, so we will just pass. And then we will, okay, just write a variable and error, and then here, okay, we will transmit the slab address first, because in the I2C bus, after the start, okay, this one is start condition, first, okay, address is sent, so we will send address. So to send address, we will, okay, store I2C1, we will store, okay, I2C1, this is the register where the address is going to store. So this function, this line is saying I2C1 is now using this register, and this register, in this register, the slab address is going to store. The slab address will be stored, okay? The slab address will be stored in that MSA register. And this one is saying, okay, the slab address is a 7-bit address, and it can be stored from the bit 1 to 7 only, okay, not in the bit 0. Let me show you. Yeah, this is MSA registers, and here, okay, the slab address can be stored from 1 to 7 only, because this is 7-bit address, and this 0-bit we cannot use for storing the address, because this one is for detecting whether we are receiving or we are sending to the slab device. So because of that, 0-bit is not used for storing the slab address. So slab address here we are using is 6, 8. That one is 6 and 8 is 1000. So this one is 6 and this one is 8, and the slab address we are using is this one, right? For the GS1307, that slab device, the real-time clock device. Okay, and so the slab address is this one, and it should be stored from bit 1 to bit 7. And so bit 1 to 7, that we will write 0 here, so this is the 0 bit, and we are putting the address from bit 1 to bit 7 only. That means we are here shifting 1 to the left, and then from here we are here putting the address from bit 1 to 7. So we are shifting 1 to the left, we are shifting to the left only 1 times. We are shifting to the left only 1 times, so 1 bit. So we are shifting to the left only 1 times. Okay, and then put the address from bit 1 to bit 7. So we are putting the address from bit 1 to bit 7. And then here we will store the memory address, of, here we will store the memory address of the that one. First, in the slab device there is RAM, okay, RAM memory, and here we will store the those memory address. And so this memory address will be 0x00. Okay, because this memory address start from 0x00, and the slab device, the GS1307, the real-time clock device. And then so this address, okay, so this address will be stored, this one is this address, okay, this address will be stored in the MGR register from bit 0 to bit 7. From bit 0 to bit 7, and okay, so from bit 0 to bit 7, because this is the register where we are going to store the data that is going to transmit from the master to the slab. The address is also a type of data. Okay, so because of that we store that address here in this MDR register and will be transmit through the I2C bus, because whatever we are going to transmit, all those data we have to store here and then transmit through the I2C bus. And then since we have slab address, memory address, we will start the transmission. So we will write means 0011. So this bit is run bit and this bit is start bit. So MCS equal to 3. Here we are writing the slab address for the first time to choose a particular slab device, and we are writing here that means we are writing that means we are transmitting. So we are writing, we are transmitting, and so because of that this MCS resistor will be used as write control resistor only, as we are writing the data. Writing means we are transmitting the data. So this MCS resistor will be used here as write control resistor, and then we want to transmit the data, so we will choose this run bit and then start bit, as we want to start transmission of the data. Run means perform execution of everything that is required, and start is start the transmission. We will choose these two as we want to start the transmission. So here the start bit is set already here, so we will start the transmission. Wait till the so this function will be called, and I will write this function. And what this function is going to say is, as here the value 3, this one is the start bit and this one is the run bit. So the start bit is here, so the transmission will be starting. So transmission will be starting in the soon. So in the next line the transmission will be start. So this is the next line, and this function is going to be this, right? So we will write here as the transmission is going to start, that means transmission going on means the bus is busy. So we will say while the bus is busy, while the bus is busy. So this what this line is saying, while the bus is busy means while the I2C is using this MCR resistor, and this MCR resistor value is equivalent to 1, means 1 is 1, the meaning of 1 is the busy bit. So it is referring to busy. So while the bus is busy, here the bus is busy. Here the bus is busy. So what does it means? The bus is busy means the status is busy. The bus status is busy, right? we know, okay, the bus is busy because after we know the status of the bus is busy. Status of the bus is busy means we are reading, okay, the status of the bus. Okay, so we are, okay, using MCS register here. So MCS register is performing the reading of the status of the bus as busy. That means MCS register is now used as performing, okay, the reading, okay, operations. So it is now used as read-only control register. Okay, MCS is now used as read-only control register because we are reading the status of the bus, okay, as, okay, the bus is busy. Okay, so that's it only. Okay, the I2C is now using MCS register and read control register, okay, used as read control register, and used as, okay, that first bit that is busy, saying, okay, the bus is busy. That's all. And well, okay, the bus is busy, that means when the bus is busy when the transmission is, okay, going on. Okay, so during the transmission, okay, here we are sending, okay, the address, right? We are sending here, okay, the address. So after that, after, okay, the start condition, transmission is going on, so the bus is busy. So okay, here we are sending the address, and after that we check the acknowledgement bit. So we will check the acknowledgement bit here, return I2C 1 implies MCS and 0x8. So here, okay, we are checking, okay, the acknowledgement, address acknowledgement bit, and okay, the line is saying, okay, I2C is now using MCS register, and this MCS register is now, okay, equivalence to E. E means address acknowledgement bit, data acknowledgement bit, address acknowledgement bit, data acknowledgement bit, address acknowledgement bit, and error. And we're checking the bus is busy, so if there is any error, the bus is busy, if there is any error, and error is usually caused by either the data acknowledgement bit or address acknowledgement bit. So if you want to check error, this 3 bit is usually checked, because error is usually caused either by data acknowledgement bit or address acknowledgement bit. So that's the way how, okay, error is checked, by checking this 3 bit. 3, okay, means 111, that is, this one is not checked, so 1110 means E. So because of that, okay, I'm writing here, okay, I2C is now using MCS register, and MCS register is equivalent to 0x0E. Okay, E means data acknowledgement bit, address acknowledgement bit, error, and this one is 0. 0 means busy bit is not, okay, we are referring here because we are checking only the error. And then, okay, here MCS register, while the bus is busy, right? So we are checking when the bus is busy, we are checking if there is any error. So we are reading if there is any error or not. Checking means reading, right? So, and also while the bus is busy, So we are doing MCS register the reading functions. So because of that, we are using this MCS as read-only control register here. Okay. And then checking if there is any error, because we want to check the address acknowledgement bit to know whether the address whatever we have sent, all those address is acknowledged or not, because the address we have sent, we check if address is acknowledged or not during the data transmission. So we will check the address acknowledgement bit only, not the data acknowledgement bit, because only address acknowledgement bit is checked after transmission of the address in the data transmission process in I2C. Because of that, we will not check the data acknowledgement bit. We will check, so data acknowledgement bit is not used, so its value will be 0. Address acknowledged, then its value will be 0. If address is acknowledged, then error will be 0. Here we are not referring to BC bit, so the bit will be 0. If there is any error, that data acknowledgement bit we doesn't check here, so we check address acknowledgement bit. If address is not acknowledged, then address acknowledgement bit will be 1. If address is not acknowledged, then error will be 1. And then we are not referring BC bit here, so its bit the value will be 0. So this is when error happens. This is when there is no error. Error happens when address is not acknowledged. So here the bus is busy in transmitting all those address we are sending, and we're checking if there is any error. If error, then return the error. If error, then return the error. And then after this we will check, and here if there is any error, then this data transmission process is over again, because address is not acknowledged, then the slave device doesn't want to receive any kind of data that is going to send by the master in the I2C bus. So it is data transmission is over. And if there is no error, that means address is acknowledged, then we will send the data. We will send the data, because if when address is acknowledged, then in the data transmissions the data is sent right. That's why we will send data. So I will store the data to send in the MDR register. This is the data, and then this data is actually this value but here we are going to send one data each, one data only whenever this byte is this function I2C byte write is called. So first data will be sent only, and after this the next time this byte write will be called the next data. So only first data will be sent, that means 0x55, and after this we will start the transmission process. MCS equal to, we will write, as we are going to send only one data, we will say 5, because 5 means 101. In hexadecimal it will be this. So here I'm going to say this one is run bit. Run bit means continue whatever need to be execute whatever need to be execute, and then after that stop the transmission. One is stop it, so stop the transmission after sending this byte, after sending this data. Here when after the address is sent, the bus is still active. The bus is still active, and so we can it says run, that means we can continue the process and send this data, and then after that stop the transmission. And so we will say my keyboard is not good. We have we are saying continue the process, and then after sending this data stop the transmission. So we are continuing the process of data transmissions, and then so here data will be sent. This data will be sent, and while sending sending means the bus is busy, and while busy we will check if there is any error or the data whatever is sent the data is acknowledged or not. So this function is saying the bus is busy, that means data is transmitting, and during the transmission we are just checking if there is any error or the data is acknowledged, because after the data is sent, we check the acknowledgement bit. So this one is acknowledgement bit, this one is data acknowledgement bit. And so here we are checking, here data is transmitting, the bus is busy, one is busy bit, right? So and here we are checking if the address data so far sent is acknowledged or not. If acknowledged, then data bit will be 0. Address acknowledgement bit is not checked here, and then as we are transmitting only data, and then if data is acknowledged, then error will be 0, then no error, then we are not considering busy bit here, so busy bit value will be 0. If data is not acknowledged, then the value will be 1, and address acknowledged bit is not checked here, so its value will be 0. If data is not acknowledged, then error will be 1, and we are not considering busy bit here, so its value, busy bit value will be 0. So if there is any error in sending data, then this error will return. If there is no error, then this bit value will be returned. So here the data is transmitting and checking if there is any error or not. And so while I2C1 implies here the bus is busy in transmitting the data, and here we are checking if transmission of the data is over or not. This means transmission of the data is complete or not, because here 4 is 0, 1, 0, 0, and 0 means this. So this is bit 6, and when this bit 6 is the busy bit, of the I2C MCS register. This one is the busy bits. This bit 6 of the MCS register when used as read-only control register. Because we are choosing this bit here, because here the bus is busy, and here the bus is busy for a while, but the transmission will be finished when this busy bit is low. So here we are checking the bus. Here we know the bus is busy, and here we are checking the bus is busy, and when it is going to be finished transmission of data, and this transmission of data will be finished when this busy bit is low. Because let me just say let me just show, when this busy bit goes low, the transmission is complete after the bus is busy for some time. Because of that we write that line of the code here. The bus busy of the bus will be over, that means transmission will be complete. And after the transmission is complete, when the transmission is complete, the program should check the error bit and set it to address acknowledgement bit and data acknowledgement bit. Set it to that because it mentions set. Because the program is checking the error bit and set it to address acknowledgement or data acknowledgement bit, because error is usually caused by either of this. So we will just set it. It says error to be set to address acknowledgement bit or data acknowledgement bit. So we will just set it. Okay, we will just set it. So if there is any error while the bus is busy, error will be stored here. So we will put that error, okay, that error is okay in this variable, so this variable here, and if there is any error in this variable, as it says error to set to this bit address acknowledgement or data acknowledgement bit. So if there is error is set to this address acknowledgement bit or data acknowledgement bit, because first is data acknowledgement bit, second is address acknowledgement bit, this one is error, this one is busy bit, but we are considering only this string. Okay, if any error return error, and then the transmission will be over. If no error, then okay, return no okay error, and so okay, data and address and data will be okay transmitted in I2C bus from the master to the slave device. And where is the main function? Yeah, so here okay, in the main function, this is just an error, okay, of 7 values, okay, all these values, and we will just okay initialize the call the I2C initialization function, I2C one initialize function, because we want to set up everything for I2C, so that we can send all this data okay in the I2C bus. And then okay, after initialization of the I2C, everything set up initialized for I2C, we will okay send the we will call the function to send address and data. And here okay, we will okay pass the value this one, this is the send functions, okay, this one and all those, okay. The step address is the snap address okay is here I define, so we will pass this snap address here, and then we will okay pass the memory address, okay, here the memory address. So the memory address of the slave okay device first is 0, because this 0 is same as 0x00, okay, 0x00, and this 0x00 is this address, okay, it's the first okay memory address of the okay RAM. In the slave device there is 1307, so I'm passing okay the address here, as I pass the address here, and then after that okay I will okay pass the data, okay, this data here. Okay, I'm passing the index 0, so I will send okay only okay this value. Okay, this one is actually the address of this okay first okay this data, and when this okay I'm actually passing the address only okay of this data, and when this okay, and like that, and here okay this one sorry I'm okay passing okay this value okay, not the address. So like that, not the address, I'm passing okay this value only okay here. I'm thinking okay about the pointer okay in my mind, this one. Okay, so I'm passing okay this value here. So in this way okay this data okay will be transmitted to this memory okay to this memory inside the slab okay device, in the RAM of the slab okay device. Okay, so if you want to okay pass all this data then from the and send from the master to the slab device, then we will okay call the this okay byte write repeatedly. Okay, so I'm passing okay this data of index 0, this one, from the master to this memory okay locations, and this memory location is 0x00. okay, so if I want to okay pass this value, then okay I will call this functions byte write again, and will okay call okay this value of index okay 1. That means this okay value I will okay pass here, and then will transmit to this address location 1. 1 means okay 0x01 inside the memory RAM memory of the slab device. Okay, in this way okay we will okay pass okay to the next memory location, and the index okay 2 in the array, and then to memory location 3, and the index 3 okay value in the array. 3 is okay this one, index 3 is this okay, this value will be passed here and sent to these memory locations, and then this to memory location 4 okay, and then this index okay value okay and we'll pass okay the value 5. That means okay in this array the index 5 value, that means this one. Is it? No, this one. 0 1 2 3 4 5, this one. That is memory location, and then value of index 6. So in this way, this data will be transmitted to memory location inside the SLAP device. In the RAM memory location of the SLAP device. But here, I will write empty for loop because I'm calling this function, all this function, and this function after writing this function, I cannot just finish the main program, because if I finish, then the system will break. So because behind many things need to be done by this functions. By this functions alone, passing all those SLAP address value, memory address, and then all this data value, and then sending from the sending address first, and then data after the address, checking the acknowledgement bit. All those things are going on, and we are calling the function this byte I2C byte write many times also, so it will be repeatedly done in whenever we call this function. So behind so many processes going on. So in order to wait all those stuff, so we make the system to the microcontroller to execute this empty for loop, so that it waits to finish all those what is going on behind all those functions, calling repeatedly many times. So this is writing this empty for loop is necessary in hardware code, embedded code. So in this way, we are transmitting this data, and this data from the master to the SLAP device, and this data is, the hex value is like this. Same. 55 means 0x55, 58 means 0x58, 13 means 0x13, and just write it in the hexadecimal form. Each 5 is this is 5 is 0101, 5 is 0101, 5 is 0101, 8 is 1000 in hexadecimal, and so this binary value you will get, and this is sending bit by bit in the I2C data line to this memory location inside the SLAP device, that is DS1307. So this is how we send from the CORTEX and processor to the SD line and synchronize with the clock to the SLAP device RAM memory locations. So thank you all for this session.